So chapter 6 is systems of equations, where you have more than one equation with more than one variable, and you're looking for the solution that works for all of them. Okay, that's what we're dealing with, systems of equations. That's what chapter 6 is. I happen to like systems of equations. It's an interesting one. It is one that I apply to my other classes in more detail. They get more complicated, but this is a good introduction. We're doing solving systems by graphing. Now, I will freely admit that solving by graphing is probably the least efficient way of solving a system of equations. I'll say that straight up. It is the worst way to solve a system of equations. Unless you are really, really, really good at graphing lines and really good at being extremely accurate with doing so, it's very difficult to get a good answer. Now, the problems I give you are ones that will be easily solvable by graphing if you do it correctly, but you've got to graph them correctly. But one of the things that I like about solving systems by graphing is it shows you visually what we're trying to accomplish. Okay? Now, system of linear equations, two or more linear equations that are related to each other. Notice it says two or more. You can do a system of linear equations. Whenever you think linear, you always think a straight line. Well, you can do it three-dimensionally. Just means you have three variables. But I've done linear systems with 4, 5, and 6 variables. Does not mean that I have graphed in 4 or 5 or 6 dimensions. That's not what that means. What that means is all the equations all have, the variables are all single power variables, x, y, z. No squares, no square roots, no fractions in them, nothing like that. Okay. The solution of a system is any ordered pair or point that makes all of the equations true. Okay? Any one that makes all of them true. That's the solution. The one point that works in both equations. And this is why I like solving by graphing, because it gives you a visual picture of what we're talking about. Okay, sometimes seeing it in a graph really makes it understandable what we're trying to accomplish. Okay? And when we do things algebraically starting on Friday, what you're looking for is what we have doing it with the graph, only you're going to get a better answer, one that you're more sure of. You don't have to be quite so good at graphing. So, you have here an example, okay? You have two equations, y equals 1/3 x plus 1. That's this line here, y equals 1/3 x plus 1. That line, that blue line for me, it's black for you, but that line is every single xy coordinate combination that makes this a true statement. That's what a line is. A line is every single xy coordinate, every single xy point that makes that equation true. There's technically an infinite number of x and y combinations that will work in that equation, every single point that makes up that line. Any point that's not on that line doesn't work in there. If I pick another xy coordinate that's not on here and I plug in the x and I plug in the y, it won't be true. But every point on this line works in there. This is the line here, which is red on mine, y equals negative x plus 5. That line represents all the places that make the second equation work. Every single xy coordinate that works in the second equation is in this red line. Any xy coordinate that's not on that line doesn't work in that second equation. The solution to the system is the point they share. The one place that works in both of them. That's the goal of trying to solve a system of equations, is where's the one point that works in both equations. In this case, it's the point 3, 2. Okay, that's our solution. 3, 2. If I put 3 in here, 1/3 times 3 is 1. 1 plus 1 is 2. I put 3 and 2 in here. This is true. I put 3 and 2 in here. Negative 3 plus 5 is 2. It works for both of those. It's the one place that is true in both equations. That's what a solution to a system is. It's the one place that will work in both of them. Okay? Now, it's kind of cut off a little bit, but over here to the side, there are a couple of other examples. Okay, I have 2 other examples here. This is what happens most of the time. You have 2 lines, they cross each other. Where they cross at one point. You have one answer. This example here, where do they cross? They don't. They're parallel lines. They don't cross. For this one, that means there's no solution. If they don't cross, there is no solution to the system of equations. You have 2 parallel lines. They don't cross. They don't have any points that they share. Okay? That happens sometimes. And then it's a little hard to see, but if you kind of see what we've got going on here, I've actually got 2 lines lying on top of each other. Where do they cross? They cross lots of places, right? Yes, technically it's an infinite number of solutions. Now, it's not every single xy coordinate, but every xy coordinate that works in one works in the other. So what we say in this situation is we have an infinite number of solutions. Because every single xy coordinate that works in one equation also works in the other. And a line is an infinite number of points. Okay? You can't count them specifically. There's an infinite number of points. Okay? Questions? So the big thing we're looking at here is solving by graphing. You have 2 equations. You graph one, graph the other. Where do they cross? That's the main thing. Sometimes they don't cross. Sometimes they don't touch at all. Sometimes they touch everywhere. Usually they cross at one point. This is usually what happens. Okay, so let's do an example. Solving a system by graphing. What is the solution to the system? Use graph and check your answer. So to graph it, I need to graph the equations. There's a couple of ways to do this. First one, and this is going back and reviewing graphing equations, what we did before. Graphing this first line, what I would do is I would use x and y intercepts. If I let x be 0, I get y, not x equals 2. I get y equals 2. When x is 0, I get y equals 2. That's my y-intercept. When I let y equal 0, I get negative x equals 2. I don't want negative x, I want positive x. Divide both sides by negative 1, x equals negative 2. X-intercept, y-intercept. First point, second point. And then my line goes through those 2 points. Second equation, I need to graph that one. I'm not going to use x and y intercepts because the equation does not go well for x and y intercept. What I will do on this one is do slope and intercept. My y-intercept is negative 2. And my slope is 3. But to be able to graph it, I need to write it as a fraction. 3 over 1. From my y-intercept that I graph, I do my rise and run. I like to do my run first, so I go over 1 and then up 3. Over 1, up 3. There's my second point. I have a slope of 3 over 1. And then I graph that line. And now you can see why I don't like solving by graphing. This is what I mean by saying solving by graphing is not really a great way to solve the problems. My lines are not perfectly straight. Okay, it's not clean and crisp. Yours should be better, particularly if you have a mechanical pencil and you use a ruler. You should have nice lines and they should be better, but even then you still have to be really, really good at doing your lines. Yes, Lucas. I can figure out the slope for the other one, but the idea is graph the two lines where they cross. Now, I'm going to be honest with you. If this was a test, here's what you're looking for is where do they cross? They cross about here. And your answer, I'm not going to have it like be 3 2/3 and 5 1/4. It's not going to be something like that. It's going to be a nice, easy one to get. My solution is the point here, which would be 2, 4. And that would be the solution for this one, 2, 4. Okay, I'm not going to make you graph something to solve and have it be out in the middle of nowhere where it's hard to figure it out. Okay, I'm going to make them easy for you to do. If you graph halfway decently, you can figure out what the answer is supposed to be. I'm not going to be nasty in the equations I pick. Algebraically, it's a little easier to do that because you can come up with any number, it doesn't really matter. But solving by graphing, you've got to be really, really good to solve by graphing. Okay, you've got to be good at graphing, and you've got to be neat and clean. You got a fatty pen, and I don't have straight lines or kind of curvy. It doesn't work real good. You know, if I had a nice sharp mechanical pencil and a really nice ruler and a really good piece of graph paper, I could probably do a good job. But it's still not the best way to do this. But you see what I'm talking about. The red line is this equation. Every xy coordinate that works in here, every xy coordinate works in there. Where's the one place that works in both of them? Okay, where's the one place that works in both of them? The one place that works in both is the point 2, 4. When x is 2, y is 4. Put 2 in here. 2 times 3 is 6, minus 2 gives me 4. Put 2 and 4 in here. Negative 2 plus 4 is 2. It's the one place that works in both of them. Okay, writing a system of equations, and then we're going to use that system. We're going to solve to find the answer. So, one satellite radio service charges $10 per month plus an activation fee of $20. The second service charges $5 per month and an activation fee of $40. At what month was the cost of the service the same? So what we need to do is come up with two equations, one for each. So the first satellite service charges $20 plus $10 a month. You're paying $20 right up front and $10 a month after that. So how much I pay is $10 per month plus the $20 up front. Okay, and if I go to graph this, my y-intercept is 20, my slope is 10, so I start here at 20, and for every one I go over, I go up 10, but it's not going over one box and up 10 boxes, because it's at 1 over for each time, but 10 for each box here, so my line would look like this. Because the scales aren't the same. One per line going horizontally, 10 per line going vertically. So that is actually a slope of 10. It's not a slope of 1. It is actually technically a slope of 10. So it looks like a slope of 1. If I do my second equation, okay, the second one, service charges of $5 a month and activation of $40. It costs me $5 per month plus $40 up front. So when I go to graph it, my y-intercept is 40, and my slope is 5 over 1. So I start here, and for every one I go over, I go up 5. So actually I want to go over to here. And there's my line for that one. And where do they cross each other? Right there, at the point 460. So at 4 months, you're going to have paid $60. The nice thing is, this one is, okay, how long do I want to have this for? Which one's the better deal? Well, I'm going to pay more for the first 4 months with the second plan, but after 4 months, I'm going to be paying less. So if I'm going to have it for more than 4 months, I'm getting the second plan. Well, let's say I'm going to be moving in 3 months. I'm not going to need this anymore. And I need to want to have it for a short period of time, and after a little while, I'm not going to need it anymore. Then I'm going to get the other plan because it's going to cost me less for the first 4 months. Okay? That's what doing a system of equations will let you do. Let you figure out what's going to cost you more or less. I actually had my very first year teaching, 20 years ago. I had a student that was doing insurance for her car, and she had 2 or 3 different quotes. And because the way she was getting her insurance structured, she had the same setup. It was so much up front, so much per month. She goes, which one's the better deal? I go, well, let's do this. And we actually did this with the one she wanted to do. I said, okay, where do they cross? That's where they cost the same amount. Are you going to have the insurance for this amount of time, or are you going to have it for more than that? If you have it for more than that, you're going to pay a little more up front, but in the long run, you'll save money. She goes, okay, that makes sense. And then we did this exact same thing to help her figure out which one would be the better buy. Go, you're going to have this company for more than 6 months because it was right about 6 months. I go, if you're going to be with them for more than 6 months, pay a little more up front. Okay? Because it'll save you money in the end. She says, okay, I get that. So that's how it works. Okay, questions? Okay,